This video is for Chapter 12, Section 1. It's going to be introducing tangent lines and how tangent lines interact with circles. Now, before we start putting together what a tangent line looks like, I have to bring up that this is not a tangent that we hear about in trigonometry. The sine, cosine, and tangent ratios do have an eventual connection to this, but a tangent line in this case, we're talking more about the word tangent you might hear in English, where the teacher says, oh, you started off well, but you went off on a tangent, which means you started on the topic and you were kind of on topic, and then you skewed off in a direction that was somehow related at first, and then it went away from it. So keeping that idea in mind, here's what a tangent of a circle looks like. It is a line on the same plane as the circle that intersects the circle in exactly one point. These two lines, line AB and line CD, are tangents to the circle. They never enter the circle, they don't go in and then out of the circle. Instead, they brush up against the circle just exactly one point and then keep going. Kind of like the idea of a tangent in English. It was connected, sort of, and then it just went off. So we have line AB and line CD that are tangent lines. The point where they intersect is called the point of tangency. In this case, we have point A as a point of tangency, and point C is a point of tangency. Okay. We can have tangent rays, tangent segments, or tangent lines. So if I wrote ray AB, then it's a tangent ray. If I write segment AB, it is a tangent segment. If I write line AB, it is a tangent line. Okay. One of the theorems that we have about tangents is that if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So O to A is going to be perpendicular to AB. O to C is perpendicular to CD. The best way to understand that these are perpendicular is to realize that if you tried to connect O to anywhere else on the line, it would have to go here to the edge of the circle, and then it would have to go further outside the circle. Which means we should understand that O to A is the shortest distance between the point and a line. And the shortest distance between a point and a line is always perpendicular. So, tangent lines connected to a radius, okay, only specifically a radius, will form right angles. In an if-then form, if line AB is tangent to circle O, then at point A, then AB, line AB is perpendicular to OA. We're going to see those right angles show up in the examples that we start working with. Okay? So, note where those right angles are. We probably should draw them in our notes right now. Right angle here, right angle here. That's going to be the key to establishing the work we do next. So here's how we're going to use one of our tangents to a circle. Up on the example here, 8 is a tangent. The segment with the length of 8 is a tangent. Here's R, the radius, and here's another R right here. But here's an interesting length, 4. This is not a tangent. Okay, it's just a portion of a segment that goes outside the circle, and it has length 4. But if we know that the radius and the tangent make a right angle, we can use the Pythagorean theorem. We have a right triangle. So we have R squared plus 8 squared equals the whole length, R plus 4 squared. Now this is not an algebra review lesson, but I will make note. R plus 4 squared does not equal R squared plus 16. You have to FOIL these numbers out. You must distribute. So it will become R squared plus 64 equals R squared, and then you have to do R times 4 and 4 times R, so 8R plus 16. At this point, I'm going to subtract R squared from both sides, and it will eliminate from the equation. So 64 equals 8R plus 16. Subtract 16 from both sides, and 48 equals 8R. Divide by 8, and we have found that the radius is equal to 6. Now, if you put that number back in, this problem will probably make a lot of sense. The radius was 6, 8, and then 6 was 4 is 10. This was just a 6, 8, 10 or 3, 4, 5 right triangle that we see all the time. Okay, another example. When you have two circles that are different sizes, but we have one tangent line that is tangent to both. So 30 is tangent to both, and it's causing two right angles. One of the circles is larger than the other, and what we want to figure out is, can we find the distance between the centers of these two circles? So the way to do this is we're going to use the two right angles not to form a right triangle, but to form a rectangle. Okay? And we're going to do this by just drawing this straight down and making this rectangle right here. Since it's a rectangle, we still get the right angle here, and we get the 30 inches right here. And then the key is, what is the other length of this right triangle? Well, you have 14, and this 8 transfers across here, 8. 14 minus 8 is 6. The most common error made by students here is that they don't realize that which side is the hypotenuse. They don't realize that the distance between the centers is the hypotenuse. So we have 6 here, 30 here, and the value we're trying to find. So we end up with 6 squared plus 30 squared is equal to x squared. If we were to go through on our calculators, we would end up having the square root of 936, which comes out to approximately 30.1. It is not that much larger. So there are two examples of how to use the tangents and how they form right angles and form right triangles in the Pythagorean theorem. 30.6. All right, now look at this circle, and we've got tangent lines going everywhere here. We've got an entire triangle created with tangent lines. This introduces a couple terms that we've heard in first semester, and now are back. This triangle is circumscribed around the circle. Circumscribed goes around only touching the outside of the circle, only touching in tangent points. The circle is inscribed. That means it's the interior shape that is touching at tangent points. Okay? So the sides of the circumscribed polygon are tangent to the circle, and the vertices of an inscribed polygon are on the circle. That would look like this. I'll just put this one example on the board. Here we can say the triangle is inscribed inside the circle. The circle is the thing that is circumscribed. Now, this leads to a second theorem about tangents, which is that if we draw two segments tangent to a circle from the same point outside the circle, then those segments are congruent. Here is point B. It's connected to a point of tangency A, and it's connected to another point of tangency C. And this theorem is letting us know that that means AB is exactly the same as CB. We'll do some work with proving this in class. For now, this is a theorem that we can use, something we study and say, okay, I'm going to use this fact to help me with problems. So let's take a look at some problems that would utilize this fact. So here's one. Find the perimeter of this triangle. We know some parts, like this little part right here is 10, that part is 12, this whole thing over here is 23. So we're going to use the theorem we just saw. If a point is tangent to a circle in two spots, then the tangent part, not this whole thing, just this part from here to here is 10, so this part from here to here is 10. So I'll fill that in, 10. I'll put this one in, 12. Now, if I know that this part is 10 and the whole thing is 23, I can take 23 and subtract 10, I get 13 here. And if I have 13 here, I can put 13 over here. So now here are all the parts. I've got two 10s, so that's 20. Two 12s, that's another 24, so I'm at 44. And two 13s, which is 26. Okay, so I can add all those together and end up with 70 meters as the perimeter. Now, put a lot of this stuff together just looking at the angles of what we learned, how they form right angles, and the tangents are congruent to each other. So we have 25 degrees here. Let's look at these three angles first. ABP, center, point of tangency, tangent line, 90-degree angle. Has to form a right angle. QPA, Q to P to A. Well, A is the center, and QP and BP are congruent. BA is congruent to QA, and PA is congruent to itself. So these two triangles are clearly exactly the same. So if this is 25 degrees here, then QPA is also 25 degrees. And our final angle of BAP, well, that's this angle here, and all we have left is the triangle sum theorem. We already have 90 used up here, 25 used up here. We have 65 degrees left of our 180 degrees. So 90, 25, and 65. Now we can go to other parts like angle CAD. Well, CAD is just a vertical angle to BAP. So vertical angles are congruent, 65 degrees. How about DAQ? Well, we know that this is 65 degrees here. We know that this one here is 65 degrees. Combined, that makes 130 degrees. The semicircle is 180, so I must have 50 left over for DAQ. And finally, CDA. If I have this triangle here, this is the interesting one. This is the toughest one of these three. I know CAD is 65, so I'm going to go ahead and draw that triangle. So we sort of see this here, 65. But the key is to recognize that this is an isosceles triangle due to the radii of the circle. So I can take my 180 degrees, subtract 65, giving me the 115 degrees that are left, and then I can take 115 and divide by 2, because these two angles have to be congruent. And if we divide that by 2, we end up with 57.5 degrees. So CAD was 65, it was the vertical angle. DAQ was 50, it was left over from the semicircle. And CDA is 57.5 with the work shown here. That's it for Chapter 12, Section 1. We can begin working on our assignment.